When an object is struck, it vibrates back and forth, alternately pushing and pulling on the air around it. As it pushes, it creates a high-pressure shock wave. As it pulls, a low-pressure one, alternating back and forth hundreds of times per second. We can detect these rapid, tiny shock waves through our senses of hearing. Each wave radiates away from its source in all directions until it reaches our ears. The outer ear funnels the waves into the ear canal, leading them toward the cone-shaped eardrum. The waves push and pull the eardrum, causing it to vibrate at the same frequency as the air. The eardrum then causes the hammer to vibrate, matching its frequency, which makes the anvil vibrate, matching the hammer, leading the vibration, keeping the same frequency as the object that caused it, into the snail shell shaped cochlea. This isn't an exact illustration, but it should communicate the basic ideas. The stirrup presses into the fluid filled cochlea through the oval window. As vibrations push the stirrup into the oval window, it pushes the fluid through the cochlea. As it pulls back, it pulls the liquid back with it. As fluid doesn't compress, it needs somewhere to go, which is provided by the round window. Running along the entire length of the cochlea is a basilar membrane, which contains thousands of tiny fibers running perpendicular to the length of the cochlea. The fibers of the basilar membrane are very small, near the oval window, and increase in size as they get closer to the end. The shortest fibers have the highest resonant frequency, that is, the frequency that the fibers naturally want to vibrate. The longest fibers have the lowest resonant frequency. The fibers are connected to nerves, which are activated by vibrations in the fibers. When the stirrup vibrates at any frequency, it pushes on a similar basilar membrane, sending waves of the same frequency traveling down the fibers. So, suppose that an object vibrates at 500 hertz, 500 times per second. The sound will be carried through the ear, causing the stirrup to vibrate at 500 hertz, which sends a wave at 500 hertz down the basilar membrane. The waves travel through a number of fibers whose resonant frequencies are less than 500 hertz, and it passes through them with little energy loss. When it reaches fibers that have exactly the right length so that their resonant frequency is 500 hertz, they accept all of the wave energy and shake violently. They activate their connected nerves, sending a signal that the brain interprets as sound. The cochlea is able to measure two important qualities of the wave. First, they can measure the wave amplitude, or how widely the air pressure swings between low and high. Waves with low amplitude are a slight shudder in the air, while waves with high amplitude are pounding shock waves. Waves with too high of amplitudes can jar the bones inside the ear more than they can handle, causing damage, while waves of too low amplitude are undetectable. Amplitude is translated in the brain as volume. The harder the air vibrates, the louder the sound. The ears also measure the frequency of the waves, which translates into the brain as a pitch. Higher frequencies produce higher pitches, lower frequencies, lower pitches. High volume is detected because it's more fibers to vibrate, which causes more nerves to fire. But how does the brain know how high the frequency is? Does it measure how many nerve impulses reach each second, or does it measure which nerve deliver the message to see whether they are connected near to the start or the end of the cochlea? We don't know, but thankfully our brains do.